Hello, everyone, and happy Wednesday. My name is Alec Gapkemeyer, the U.S. Test and Measurement Product Manager for Beckhoff U.S. Myself and the U.S. team are pleased to continue to roll out these monthly webinars to discuss exciting and new products and technologies as they can apply to your test solutions. In today's webinar, I would like to focus on unpacking an issue as it relates to automated test system designs and how Beckhoff's system integrated measurement technology creates a seamless connection between data acquisition and system functionalities such as safety, database connectivity, motion, and more. And to kick it off, we'll take a look at more the traditional approach as it exists in industry today. We can quickly observe that test solutions become overgrown with many subsystems, whether it is a visual inspection component or vision system, additional sophisticated devices for maybe product handling, scaling I/O for additional DAC or control, and much more. With this, each subsystem in the design generally requires a communication interface or protocol, or even its own separate configuration in runtime software. And this essentially creates a bit of a difficulty to manage, learn, and maintain these systems, which often lead to increase in design costs and difficulties to commission and diagnose issues. This also poses an issue for R&D and test engineers when defining a transition path from capturing very high-end test specifications to a functional automated system where measurement capabilities are a little bit more tempered. On the other hand, Beckhoff's approach to data acquisition aims to simplify functional complexity and high-end integrated data acquisition. How this all comes together starts at the industrial controller. And from here, we're able to expand out on the right side into various system components like our ELM measurement modules, integrated safety, as well as compact motion. We can extend this capability out to remote racks of I/O, which retain the same ability to mix and match these functionalities. Also presents an opportunity to simplify the system a bit by presenting standard communication protocols. Say in the case of oscilloscopes, you may be able to communicate over serial communication, RS-232 or 485, amongst a plethora of other interfaces in the top right as they're mentioned. Additionally, we can use onboard integrated interfaces to connect up to vision systems, robotics, as well as connect up and communicate via IT protocols to get to cloud services or databases for logging sensor data. Also on the far right side, we can see that we can further extend this out to larger scale, say motion applications and control, as well as a front end element or HMI for visualizing the data and analyzing and running tests. And to wrap it all up, on the far left here, we have our unified development environment, TwinCAT, which draws all this together all under one hood. So to dig a little bit deeper on the data acquisition side of things, I want to unpack the measurement chain as Beckhoff is able to facilitate. First, to address our measurement hardware, it is worth noting that with the exception of machine mountable devices and in certain cabinet devices, Beckhoff's measurement chain begins after the sensing devices. Let's take a quick glance or a sampling of our measurement modules to get a baseline of what we are capable of bringing into the system. We can see a general range of capabilities for sampling rates from 10 kilosamples per second or lower, all the way up to 50 kilosamples a second. with a more lean or conservative approach to channel count per module. You can mix and match different interfaces on our multifunctional input terminals, but also gain more specific capabilities and higher sampling rates with interface specific hardware. Also, we do support the standard connection means, LEMO, BNC, standard push plug, mini thermocouples, and more. And all of these run at a 24-bit resolution as well, standard. So to dig a little bit deeper at what's actually happening under the hood for one of our ELM terminals, the sensor interfaces are received by high-end hardware filtration and circuitry to protect the signal. We then run it into a Delta Sigma 24-bit A to D converter. And finally, we're able to take that digitized signal and run it through onboard filter stages, decimation or downsampling to get the most efficient packaging of the measurement data to be expressed over our field bus, which is EtherCAT. And additional functionalities under the hood like free scaling, tear functionalities, zero offsetting, and more. And to go even deeper, to take a look at the full analysis chain or processing chain in the hardware level, we can start at the top to mention we do have a integrated sensor supply that helps alleviate the need for additional cabinet components and wiring. Also have previously mentioned our digital filter stages, which actually begin way on the bottom left here, but we're able to fit those types of functionalities into the hardware itself, so then we preserve some of the computation power at the main controlling device to do a little bit more pre-processing there. Also, we have additional measurement information as far as maybe diagnostic centric, which is indicating range errors, overage, underage, limiters that may be broken. Also, extended functionalities around load cell analysis. So you can take a signal coming in and give some very basic specifications around compression and tension, parameters, gravity, and other values to essentially present a scaled load cell value that can be linkable and used in software, as well as other functionalities, which are pretty standard around input freeze, peak hold, scaling, limiting, tear functionality, and more. And at the very end, we have usable sensor data, which we'll unpack a little bit later. And alongside high-end measurement terminals, we also do have and support basic analog inputs for applications that you may have that are not as demanding on the resolution or sampling rates, as well as embedded functionalities like accelerometer and gyroscope with the machine mountable boxes we can see here, as well as other sensing interface implementations as far as machine mountable boxes. And now let's take a quick look at some applications where this technology has been applied. And two examples of approaches to harness Beckhoff measurement technology. We have on the left an application condensing various system functionalities into a lean cabinet solution. And so we can see we have our controller, some basic I/O, basic analog inputs, compact motion driving the compression mechanism up top, as well as a single sensor line going back to our ELM terminal, all on the same rack. And on the right, it takes a much different approach. So this application is utilizing our machine mountable EtherCAT measurement boxes at various distances on the test article. This can be particularly useful when synchronizing measurements and aiming to reduce the cabling solution. Instead of having multiple sensor cables running out in a big old umbilical cord or multiple, all we have to do is mount these measurement boxes close to our sensing device and run power and EtherCAT communication, or a combination of both, depending on the product, out to each of the boxes on the test article. And to support the data transfer of measurement data, Beckhoff harnesses the capabilities of EtherCAT, the primary enabling technology for measurement technology, and the Beckhoff platform in general. And to establish a basic understanding, EtherCAT is essentially Ethernet on the fly. Sending a telegram that passes through each node, each EtherCAT slave device reads the data addressed to it on the fly and inserts its data in the frame as the frame is moving downstream. It is delayed only by hardware propagation delay times. The high efficiency of EtherCAT field bus makes it not only a well-suited measurement bus, but an already broadly adopted field bus technology for other vendors in the measurement space as well. And as an extension of EtherCAT technology is Beckhoff's Extreme Fast Control, or XFC, ensuring the measurements taken are not only very fast, but quite precise, down to the nanosecond between multiple devices. The two XFC concepts which will help you achieve time-critical measurements are distributed clocks and oversampling. So starting with distributed clocks, the concept allows you to establish a reference device clock for all other distributed clock capable devices. And so in this image, we see kind of that blue indicated R clock symbol is our reference clock, our device, which we want all other slave EtherCAT devices that support distributed clocks to synchronize to. And this process essentially allows us at the end to perform what we call drift compensation. And it's an active process between all of these devices to ensure and eliminate synchronization issues between multiple measurement devices and sensors. And a little bit closer look, if we're doing a comparison, on the top end we have a standard analog measurement terminal. And we can see that from cycle to cycle that there's an obvious impact on jitter and stability as it results in, say, this would be driving a positioning for a motion application. You can see that there's quite a bit of variability between cycle to cycle, where on the bottom, a implementation with XFC allows a constant measurement between each cycle, resulting in more or less kind of constant or stable control. Another supporting or complementing technology from XFC is oversampling. And so each of the measurement terminals are taking the full breadth of sampling, and at the terminal level we can specify what the equidistant amount of measurements within that time frame we want to extract. And it provides us, again, equidistant measurements leading to very fine feedback. So on the top left side, we can see a standard machine has more of a jagged or discrete result, whereas on the right side, we have a much more continuous flow and much more information that we're getting from our application. And so an example where this could be useful is in maybe weight dosing. High volumes of products are being produced but a traditional measurement would maybe induce variability as a overage or underage of product. And this may lead to either a cost to the manufacturing company in their process as they are over providing products, or it could lead to a customer complaints where there is a shortage of that product, and the complaint being the customers being undersold. So oversampling stabilizes this uncertainty and can be paired with other EtherCAT capable DC devices such as our servo motors and drives, which would help achieve a perfect amount of product for each and every cycle. So now let's connect to an actual system and see the first steps in the process for utilizing the measurement chain. On my I/O rack, I have a few sensing devices, a couple standard I/O, and a coupler, which is then communicating EtherCAT back to our main controller, our industrial controller, which has EtherCAT runtime on it as well. And so what we want to observe here is we're starting completely fresh with nothing connected. And what does it take to go from what we call as a file new to a usable sensor data to analyze in your system? So again, the objective here is to see the flow. So in this case, I'm going to bring in or bring up a TwinCAT project, brand new. And I want to make a connection to my main controller so I can actually start defining what the parameters for my measurement terminals should look like and also bring that data into TwinCAT. And first I'm going to go ahead and set up the real-time setting. So I actually want all of this to be on a specific isolated core that's specifically running a task linked to it with no other interruptions. And I want to present a linkable array where I can land all of my measurement data as we're communicating it not as each individual data point, but as an entire array of oversampled data. So I'll add a couple of these defined inputs. I'll do one for the load cell here as well. And the size of these arrays are specific to the amount of oversampling I'm going to be specifying once I get down to the hardware. So now I'll go ahead and scan in any of the EtherCAT devices on my network. And so on the bottom left side here, we'll be able to see that we can scan in for what we call boxes or devices. We can go into each of our measurement terminals and we can specify the oversampling. So 50 for the vibration sensor, and we'll do later on 10 for the load cell. And now I can go in, and this is the interface to specify your measurement range, your interface. For this case, my IEPE AC coupling and my bias current as well for allowing my vibration sensor to function. And then I'll also go ahead and link the data object to what I had defined up top with my task. And I'll do the same process too with the other terminal. And so with this terminal, we'll actually be able to see as we expand this open, all the supported interfaces, as this is one of the multifunction modules. And this use case would be maybe instead of having to invest in multiple terminals for specific interface types, we're able to parameterize each individual channel functional to what sensing devices we want to use. So I'll go ahead and activate my system to get all of my measurements live. And I can go back in and some of the information as I expand it out here, I can actually see the raw values in various points in the process, the analysis chain. And I can also inspect the effective sampling rates, temperatures, CPU usage, and many more diagnostic pieces of information. Same thing with the other multifunction terminal as well. So I was able to effectively validate that the sampling rates that I've specified or are aiming to set up for have been achieved. And I can also see that there's other diagnostics for all the other components, even up to the EtherCAT network side of being able to identify functionally, is everything working right? So now that our data has been brought in, it's been digitized, and in software, I'd like to turn our attention towards the capabilities in TwinCAT to post-process, log, and even pipe the data to other supporting tools for analysis. And to start and call it out, we have various tools that are embedded, again, right into TwinCAT, like TwinCAT Scope, to visualize our signals and any other data points from anything else in our target system. Filter Designer to allow us to make custom filtration for regions of interest or maybe specific filtration of data that we do not want to see as it comes into TwinCAT. Also, we do support power monitoring, condition monitoring, and other runtime libraries for these functionalities during maybe production tests. Also, we do have interfaces for LabVIEW and MATLAB Simulink that use what we call ADS, and it's a means to be able to pipe data between the two platforms to enable the use of those tools as well. So let's expand on some of these capabilities, specifically signal filtration, signal analysis tools, and an example of how to connect a familiar measurement tool to our Beckhoff measurement chain. So first, starting out and earlier in the hardware details, the mention of filtration was possible on board with Beckhoff's measurement terminals. The implementation of signal filtration ranges from basic selectable filters on the left here for maybe commissioning or some basic noise with a couple notch filters. Working further up, we do have full capability for you to be able to design in specifically the cutoff frequency, order, type of filter, fully parameterize and analyze filters for more specific uses, all the way up to the expert level, which is a third party or custom built filter designer. And the output of that is centric around filter coefficients, which those coefficients can be drawn in and planted on the ELM terminal itself as well. Furthermore, getting into some of the post-processing tools on the left, we can see we have kind of a brief mentioning or a short list of tools from real FFT to sliding DFT, magnitude and spectrum analysis, statistics, kind of all the tools that you'd expect to be in a standard signal processing toolkit, if you will. These can be combined in any specific measurement chain for analysis. What we're seeing here is actually an integrated tool called Analytics, which there will be another webinar to expand further on these capabilities, but this is more or less the visual representation of all of these tools together, which draws in the signal sources, visualization with the integrated scope, and a drag and drop toolbox to be able to chain together appropriate tools for the analysis you're trying to perform. And in some cases, existing frameworks of code or carefully developed algorithms may exist still and are just too difficult to get away from or convert. If you need to pipe the data from TwinCAT to those hardened tools in your measurement chain, the TwinCAT to LabVIEW interface creates this pipeline for data exchange, but can be used more than just a vessel for measurement data. There's a high potential for allowing it to be a means of control to further harness any of the functional extensions that exist in the Beckhoff platform, I'll say. Something worth noting here as well is with our Beckhoff IPCs, you are able to plant both a LabVIEW runtime or executable and TwinCAT on the same device without having to draw in a additional third-party PC or standalone PC. So, picking back up from where we left for the hardware demonstration, what I'm going to do here is showcase kind of the ability of what our integrated scope is capable of doing. So right here, I'm going to go ahead and point to our target system, and I'm going to draw in our measurement data. Now it's worth noting here, I have taken that data and scaled it in PLC code to make it presentable and scaled to something that makes sense. So what we see here is essentially I'm testing out to make sure that all the settings in my system is functioning right. I'm getting data points. I can also zoom all the way into the time scale for our PLC cycle or driving cycle time. And we can actually validate that we are getting the appropriate amount of data points for each of the signal interfaces as we could count it out. So it'd be 10 on the top for the load cell in green and 50 on the bottom for the vibration signal. And so I'll resume our scope measurement, and I'm going to go ahead and induce a disturbance or an imbalanced load. In this case, it's simply just in the form of a fan. And so I want to go in here and add a couple time markers and identify what the fundamental frequency is of this load as I'm running it at the lowest speed, I'll say. And so I can get a time difference between 2 points. And so I'm going to approximate that at about 30 hertz is where I'm going to want to start my filter designer. So I'll go ahead and bring that in now. And I'll define what my cutoff frequency is, increase the order a little bit. And it's worth noting as well is that you can plant these filters in not only I/O, but also directly in the PLC as functional filters as well. And so I'll go ahead and make a couple copies of these filters. Maybe I want to test out a few different filter options, cutoff frequencies, orders, just to test on my system. And so now I'll drag and drop side by side our filter designer right along with our scope project as it's running. And I'll go ahead and directly apply to the specific channel this design filter. And I'll just kind of go through starting from 50 hertz all the way down to 25 hertz. And so we can see live, I am still actively pushing all of these filters while the data is incoming. And so I'll go ahead and remove that filter from the specific channel. I'll pause our measurement and scope, and I'll zoom in so we can do a compare and contrast between our design filters and how they're applied in a smooth signal to a very noisy, dirty, and probably unusable signal. Right. So, circling back around on what was accomplished today, we explored a broad overview of benefits when it comes to the automated test system design. Also, the benefits of Beckhoff measurement chain from hardware all the way down to the pre-processing tools at the module level to expose the software, and finally, functionally, how the workflow looks from fresh sensor, new design, new setup, all the way to usable data in TwinCats. And just a few closing thoughts. If you'd like to learn more, please feel free to reach out to me or your local Beckhoff representative. On the screen, we have two QR codes. On the right is contact forms for more information or discuss an application. And on the left is our webinar series registration page for upcoming webinar topics. The next being XTX with Jeff Johnson. Also worth mentioning in a few months or early part of next year is the analytics webinar with Brandon Stifler, where he will expand a bit further on the tools as they exist in analytics and what that workflow also contributes to the measurement chain. All right, and to end with a little bit of Q&A, a few questions here. Are the data acquisition modules only able to function on its own rack? No. They can be intertwined with any other system functional terminal, distributed. You have full flexibility when it comes to that. How does XFC synchronize with other devices using IEEE 1588? So we can add an EL6688 terminal, which is specific for this function, and that would be planted right on the EtherCAT network. And the terminal can be a PDP master clock or slave, and using EtherCAT distributed clocks, which I had gone over previously, it can be used as the reference clock in that process. And it's fairly automatic, little configuration. If you have more interest, please reach out. Is everything measurement related for TwinCat BSD available as well as Windows? Correct, yes. All functions are released for both operating systems. If you're looking for something specific, we can look into it. I'm fairly certain. Yes, it is. Do you need to acquire a license for the data analytics on TwinCat 3? For testing and development, you can create a 7-day trial license, which you can freely renew to work with all of these tools. When it comes to a more permanent installation of a test system, we would recommend getting a license for the target system. If you want more information, please let us know. And do you have any recommendations when implementing Keyence laser micrometers, or does Beckhoff make something like the Keyence laser micrometers? We'd want to take a look at what the operational requirements are to have that type of device function in our system, and as well as the output from that type of device. So if it needs some kind of special amplifier, it may become a little bit more tricky, but if it's a standard electrical interface, some voltage coming out that can be represented by what is actually measured or being measured, we may be able to bring that into TwinCat and perform that. You showed 3 types of areas for filtering: COE, filter designer, advanced filter design tools. Would a Kalman filter be classified under advanced tools? Yes, it could exist as a custom filter in Filter Designer. I know that we have a library as well that supports that, but it's for like positioning algorithms. Otherwise, yes, a third-party software could be utilized as well, like a MATLAB Simulink with an interface or as a TC-COM object, which would function real-time in TwinCAT as well. So we do have a couple options on that front. And lastly, what tools for post-processing the measurement data does Beckhoff have? Are there any centric around predictive maintenance? Yes, the toolbox that I had alluded to earlier not only lives as a, we'll say more of a visual implementation in TwinCAT Analytics, but also as a PLC library, and that would include tools again like sliding DFT, real FFT, spectrum analysis, Sepstrum, all the standard tools. Also, there are supporting libraries for like power monitoring if you're doing THD analysis or performing some further analytics on your voltage or current measurements in your system as well. If you have any other questions, please reach out. Again, there's another webinar around the corner for expanding on some of these topics. This was just covering more or less the top layer, how to, why to measurement basics with Beckhoff. So again, thank you for your time and have a great weekend.